Okay, so yeah, welcome to this week's seminar. We have two speakers. We're going to start off with Hart, who is one of Dal's own, has an ocean science degree from Dalhousie, and now you're working here on your MSc, and you're talking to us about modeling and all sorts of stuff. So feel free just to take it away.
So I guess I was feeling, when I came up with my title, I was feeling poetic. I asked my writer friend if the reference in the title was obvious, that it was obviously a Steinbeck reference to Of Mice and Men. I had this whole plan to include all the themes of the structure around that, but he said he didn't get it, so we'll just pretend that never happened. But yeah, so today I'm going to be talking to you about one of the chapters of my thesis, focusing on aquaculture waste and the fluxes of organic carbon that it sends to the sediment and the responses of the early diagenetic processes of the benthos. Now, federal and provincial management for aquaculture outline a combination of both reactive and proactive monitoring and waste mitigation strategies to address both environmental and fiscal sustainability. Proactive modeling influenced strategies exist mostly during initial site assessment and assessment of site expansion. It isn't an ongoing thing. It's just when one of those two happens. The ongoing monitoring that does occur involves things like bottom photography and sediment grabs, which measure things like the physical, geochemical, and macrofaunal aspects of the sediment. Now, the idea for this tool, the regulatory software we're hoping to create, is that it's going to be used in conjunction with the annual site monitoring, and it's going to be putting that data to work, putting it into the model, and over time making it more accurate and precise, and helping it predict ongoing. That's a quick rundown of what the software is going to look like. It's called FINS, which stands for Farm Interactions in Natural Systems. I'm partnered with Longline Environment Limited in the UK. Now, Longline's been working on the hydrodynamic model, which uses FVCOM, and organics, which is a waste deposition model. And personally, I'm building the early diagenesis model. Now, my knowledge on FVCOM and organics is limited, so it's just because I haven't been working in the guts of that kind of stuff for my thesis. In the future, when the thesis is done, I'll be addressing this stuff a little more. If you do have any questions about how those operate, I've provided a couple of papers here if you want to follow up on that. This is just kind of a logic model of how it takes the hydrodynamic model and the cage setup, puts it in, then we get our organic matter flux, and I give us sulfides out of that. Just a quick rundown, quickly show you some images of the software, how it looks in its alpha state right now. We'll be taking variable dosimetry. Sorry, this is Liverpool and Shelburne. Then we add in our connectivity, currents, wind, all that stuff. And then from there, we look at our cage design, duplicates, templates, and all that stuff. Plenty of freedom. Then after our cages are designed, input things like fish stocking density, feeding schedule, feed type and size. From that, we get our fluxes to the sediment, our grams of carbon, our contours, and I take this organic matter carbon, put it into the genetic model, and get dissolved sulfide concentrations and remaining carbon that hasn't broken down. Now, why sulfides? The sulfides are used as a proxy for sediment health, both in our province and in other regions as well. And from this and other things, as you can see here, from sediment color, microbial presence, and the like, this benthic enrichment index allows us to create a sediment classification scheme. So depending on what the mean values of the monitoring are annually, you get placed into an oxic, hypoxic, or anoxic category. Depending on which category you're placed in, the government will make decisions on perhaps you need to change something to mitigate your waste load. Now, so sulfides, it's used as a proxy for sediment health, and it's also closely related to redox. However, this relationship weakens the closer we get to oxic classification. So redox acts as a quality control for sulfides and vice versa. And though not great on their own, organic matter percentage and porosity percentage provide good indicators of the difference between farm and reference sites when combined with redox when sulfide measurements are insufficient. Sulfides can be quite variable and volatile at times. I'll quickly run through how I've chosen to construct my model. On the right is a cartoon that I'm sure a lot of you are familiar with the classic vertical zonation of the benthos. Now, when you get high organic matter loading to the sediment, this can change the domain size of these zones and can push post-oxic and oxic zones, either eliminate them or push them so close to the surface that they're just relatively inconsequential layers. So for my model, the assumption is that nitrate and manganese reduction are reserved to the earlier stages of organic matter loading, and any influence they would have on the sulfur cycle or the degradation of organic carbon is inconsequential. However, things like dissolved iron ions and iron hydroxide heavily influence sulfate reduction rates, so they were maintained. Again, classic diagenetic equations that a number of you are familiar with. We have different transport processes for solids versus solutes, and solutes have an irrigation term here. Now, for the provincial monitoring, these classifications are based on the characteristics of the upper 2 centimeters of sediment, and I'll be addressing and showing some of that in my simulation results. So some will be the entire column, some will just be the upper 2 centimeters. Now, what might be a little different from the equations you've seen before is that this KV value here, right beside the bioturbation coefficient and the irrigation, this KV value was added as a sulfide toxicity control on the biologically mediated transport. So I've got just the different values that would exist for it. Everything would occur as expected for anything below 1500 or oxic categories, and hypoxic things would decrease until once it's greater than 6,000, or the anoxic category, the biologically mediated transport would cease completely. So I'm working with the cycles of the organic carbon, iron, sulfur, and oxygen. Now, this species relationship map I have up here, there's still a lot going on. There's a lot of reactions and a lot of different species, organosulfates, amino acids, zero valent sulfur, polysulfides, intermediate sulfides, lots of things. And if we're going to be modeling a large area, it's going to be a lot of cells, maybe hundreds of cells at a time. We need things to operate rapidly and efficiently. It takes a month for the model to run. It's not a very useful regulation tool. So over time, I've been stripping out more species and reactions, the ones that are relatively have low impact on the outcomes. So this one down here is kind of an example of, well, this is going to be what the simulations you're looking at today are based on. But in the patent, which gives us about 8 or 9 species, depending on if I have variable reaction velocities for species that combine with ferric hydroxides, and how many organic matter pools I have, labile, semi-labile, and refractory. And that just that just means the decay rate of them, refractory being a decay rate of 0. I'm just going to quickly touch on variables and parameters in my model. Now, the majority of parameters are independent both of space and time. However, things like porosity and bioturbation are depth dependent. Porosity, as you get deeper in the sediment, the volume fraction changes because of compaction. And bioturbation, there are different relationships that bioturbation has in the literature, quite a few, to things like sedimentation velocity. Sedimentation velocity is how the advection through the sediment, both of solutes and solids. So I have my porosity. I've chosen for it to be independent of time, so it's going to be consistent throughout time, but as it gets deeper, it'll change. Now, this is called steady state compaction. And for this to be true, you can see the sedimentation velocity equation is based on the organic matter flux, and that allows for mass conservation to maintain the porosity as the original profile. The only issue with that is in aquaculture farming, there's generally a year and a half of farm stock and then 6 months of fallowing where the farm is not active. So obviously, when the farm is not active, we're not going to be having a flux from the farm, which would impact certainly what this would be. However, for the simulation results I'm going to show you, the fallowing period, the sedimentation velocity will be the same as it is for farm activity. So as a means, I need to pick some values to as endpoints for my model for the fallowing period. So I wanted to get the field monitoring results, and I have some of them from Shelburne Harbor. There's 4 different sites there, which have varying degrees of activity over the past 15 years, from 2004 to 2019. Annual results, except for some stuff I did in 2018, 2019, which is far more in depth. And then I've indicated sources of fresh water and wastewater water treatment plant here as well. So these are our annual values for organic matter indicated by LOI and dissolved sulfides on the right. Now, the mean value seems to be around 20% over the years, and green indicates the reference site. And if you look back down here, you see that the sediment classification for organic matter is based on the multiple of the reference site. Now, the relationship, because sulfides are volatile and aren't necessarily representative of the amount of organic matter breakdown, the relationship isn't perfectly linear between the increase in organic matter and sulfide concentrations, but I'm using these means and standard deviations as, can my model at the same time hit between 40 to 50% organic matter concentration and around 7,500 or 10,000 micromolar. So I'm just going to run through some simulations I've been doing. I've been changing a number of things: irrigation depth, input flux, coefficients, and things like that. So for these first ones I'm going to show you here, this is different input fluxes from the farm. These are micromoles of carbon per centimeter square per day, with a decay rate of a high decay rate of 1 per year and a semi-labile at 10 times lower. So you can see this is the oxygen respiration, or the breakdown of the organic carbon that's coming by in the upper 10 centimeters, which is for my irrigation depth, the biologically active layer. You can see here as in the high, the fluxes with the cooler colors in the green, we get this drop here indicates the beginning of the breakdown of the biological activity, or the reduction of the size of the irrigated zone. And I could show that here with our flux 75. Sorry, I didn't put a label. This is hydrogen sulfide. Category here, anoxic, begins at 6. So this would be hypoxic levels here. So you can see where it gets broken down. Biological activity stops here. 75. This is like the 75 here this day, and as the fluxes increase, the breakdown is sooner and sooner. So for dissolved sulfides, they need fuel to create these sulfides, and that comes from things like sulfates, which is not as desired of a breakdown metabolic pathway as oxygen, but once oxygen is used up, then sulfate becomes the next best thing. Lots of sulfate in the water. However, if something like the irrigation breaks down, and then sulfate isn't as available, then once you get down there, it takes a lot longer for the sulfate to replenish through, if it's just strictly advection and not biologically mediated. So, and I'll address more of that in a second. This dashed line is the period of fallowing, so 6 months. This is our active farm, and then our fallowing period right here. So here you can see this is and H2S represents both HS and H2S, our dissolved sulfide concentrations. And you can see here quite a rapid drop once fallowing begins here at these high flux levels, and that initially seems quite positive, but it's actually because of the rapid drop in sulfates are not available in those upper 2 centimeters. So this one right here was the upper 2 centimeters, but when we look at the entire column, we can see that the hydrogen sulfide is increasing throughout the entire column, and even down here at the lower input flux rates. So we've got our hydrogen sulfide in the upper 2 centimeters. Now we want to look at our organic carbon. Now I've got maximum organic matter concentrations and minimum organic matter concentrations. And when we measure the upper 2 centimeters, we measure all organic matter. It's loss on ignition. So the reason I have a max and a minimum here, and this is based on the carbon composition of organic matter. And that can be somewhere from 28% by weight to 60%. So if it's at, 60% organic carbon, then we'd have lower concentrations, percentages, and higher percentages. So you can see here, we were looking before at the Shelburne results, and they were 7,500 to 10,000. So these don't quite hit there even with very high levels. So we need to make more hydrogen sulfide, so I thought I'd address things like decay rate. So when increasing the decay rate of the organic carbon, I guess start to get much higher concentrations of sulfides because they're breaking down much more rapidly in a smaller area, increasing the concentration. In much higher values here, and at a higher decay rate here, kind of closer where we want to be. We've got 40 to 50% on the minimum and things like that. So these are getting a lot closer where they need to be. Just got to tweak a few more things. I have different simulations other than changes to input flux, where things are getting a little bit closer. But that is bringing me to the end of my time, so I'm just going to quickly talk about future work. My sediment profiles are based on the literature currently, because the domain of my model is 50 centimeters, not just the upper 2 centimeters. So they're based on the literature of areas of anoxia with similar profiles. But it would be wonderful to get sediment cores for further validation from the area, and then deal with potentially resuspension, because the amount of organic carbon available for diagenesis would need to be lower than the results I've been getting from the flux models before. Yeah, that's it. Thank you.
Great. Do we have any questions out there for Hart?